alternative way, which uses what's called the log likelihood ratio. Now notice one thing in particular, which is that the messages we're passing, so for instance from a variable to a check, they're all functions of binary random variables. And ostensibly, they're probabilities. That doesn't always work out in practice because we don't always renormalize, but they should be probabilities up to normalization. So u of xi is equal to, takes two values, mu of 0 and mu of 1. Now, if this is a probability, in fact, we only have one value to worry about. So in fact, all of these messages can be represented as real numbers. Which means that if we have any real number that can be mapped back to a probability, we're free to express it in those terms. So what I'm going to use instead to represent these messages is a single real number called the log likelihood ratio. The log likelihood ratio basically looks like this. It's log. The base is usually e, although it doesn't matter. Well, actually, it does matter in our case, so let's call it natural log. It's log base e of the probability that x is 0 divided by the probability that x is 1. So I'm going to use shorthand notation. So that'll be log, it's called p0, the probability that x is 0. And the probability that x is 1 is therefore 1 minus p0. So log likelihood ratio is often used in decision theory, and it has lots of nice properties. For example, the range of this value is from minus infinity to infinity. It's equal to 0 if p0 is a half. So in other words, it's only equal to 0 if you have no way to distinguish, or if you can't really distinguish between 0 and 1. And the closer it gets to infinity, the larger p0 is, and the closer it gets to minus infinity, the smaller p0 is. So therefore, the closer it is to infinity, the more you believe that x is 1, x is 0, and the closer it gets to minus infinity, the more you believe that x is 1. And in fact, if p0 is 1, in fact, if you're 100% certain that x is 0, what is this? It's 1 over 0, which is infinity. Log of infinity is infinity. On the other hand, if you are certain that p0 is not the case, then this is 0 over 1, which is 0, and log of 0 is minus infinity. So those extreme values are also important. So how does this impact our calculation of messages? Firstly, I'm going to say the following. How do we get from, so we've seen how to get from p0 to L. L is log p0 over 1 minus p0. How do we invert that? In other words, how do we go from L to p0? Well, let's solve for it. We have e to the L is p0 over 1 minus p0. So therefore, 1 minus p0 e to the L is equal to p0. So e to the L is equal to p0 times 1 plus e to the L. And finally, p0 is equal to e to the L over 1 plus e to the L.
Could you repeat that? You heard that? I couldn't catch. L and P0 is the previous probability, isn't it?
Yes. So I'm just inverting the calculation. I'm saying L is a function of P0, so how do you invert the calculation? If you have L, how do you get P0?
L is the, which value is L?
L is the log likelihood ratio.
Oh, okay. You just define it here, sorry.
So,
And wasn't it, I'm sorry, wasn't it the log base 2? How,
no, it's log base E now.
log base E?
Yeah, in fact, let's emphasize that. Because normally log means log base 2. So let's emphasize that this is log base E. Actually, it doesn't matter. You could still use log base 2, but in that case, this would be 2,
There'll be a factor.
you know, and there would be a factor. So whatever. Anyway, excuse me. Where was I? So at a variable, what do we do? So I have L of x1, L of x, L of x, L1 of x, L2 of x, and so on up to L dv minus 1 of x, where Li of x is equal to some probability. Basically what this is natural log of, whereas before I had the message mu I of x, this is natural log of mu I of 0 divided by mu I of 1. So that's just the log likelihood ratio form of the IF message. Similarly, I have the channel, let's call that LC, remembering that this factor is f of yi given xi, where yi is plugged in. LC is equal to natural log of fyi given 0 divided by f of yi given 1. Mu out of x. What? Excuse me. What I have is L out of x. L out of x is natural log of f of yi given 0. So this is natural, excuse me, let me back up. This is natural log of mu out of 0 divided by mu out of 1. Mu out is equal to f of yi given xi, so in the numerator I have fyi given 0 times the product from I equals 1 to dv minus 1 of mu. I'm overusing I here, I used j before. So let's continue to use j here. Of mu j of 0 divided by f of yi given 1 product j equals 1 to dv minus 1 of mu j of 1. Now, because this is log, I break up the products into sums.